So today we continue on the Cauchy-Schlomlich transformation, and the aspect we'll be focusing on is the application bit. The problem that I think will be of interest for us today is this integral, which we call I, being equal to the definite integral from x equals to 0 to x tending to infinity of cosine of ax over b squared plus x squared. And this happens when a and b are all greater than 0. This problem here is part of the problem that are in the book Almost Impossible Integral Sums in Series. And this is problem 51, but since this is an extension of our previous treatment of the transformation, so we would like to dub this as problem 51b. So before we move forward into the solution part of this video, I'd like to encourage those of us who have not subscribed to our channel, please do consider subscribing to our channel. Your support will go a long way in giving us that extra profile that we do need. And if you do like what we're doing here, please don't hesitate to leave a like. If you know somebody might benefit from what we're doing here, please do also not hesitate to share this video. So without much ado, we're proceeding forward to the solution phase of this problem. This happens to be our problem, which is I equals to the definite integral from x equals to 0 to x tending to infinity of cosine of ax over b squared plus x squared. Now we can derive 3 more problems from this problem, and so we would like to name the second problem that we can derive from I as being equal to the negative of the derivative of I with respect to lowercase a, which is equals to negative derivative of a, the integral from 0 to infinity of cosine of ax over b squared plus x squared, which is equal to negative 0 and this I mean we can use partial derivative, but let's just do that. Dx, so which is equal to negative 0 infinity negative x sine of ax over b squared plus x squared is equals to x sine of ax over b squared. So that is j. So we're going to also solve for j, and we'll follow up with k, which is equal to negative 1 over 2b, the derivative of I with respect to lowercase b, which is equals to negative 1 over 2 small b, the derivative with respect to lowercase b of that integral cosine of x over b squared, which is equals to negative 1 over 2b cosine of ax derivative which is equals to negative 1 over 2b 0, and that becomes cosine of ax negative 2b over And you see this and this, this and this, and this is squared, so this becomes 0 to infinity cosine of ax over b squared x squared squared. So that is our K problem. And then lastly, we want to look at the L problem, which is going to be -1 over 2b, the derivative with respect to b of j, which is -1 over 2b, the derivative with respect to b of the integral from 0 to x tending to infinity of x sine ax over b squared plus x squared, which well, let's maybe delete that for now and say that propagates inside equals to 1 over 2b. See this and that and that and that, so we're getting and so we're going to solve for with this as just a derivation. The main problem is problem number 1, which is I being equal to the definite integral from x equals 0 to infinity of cosine of ax over b squared x squared. Number 2, j is equals to integral of x sine ax over b squared plus x squared. 3, k, which is equals to definite integral from x equals 0 to x tending to infinity of cosine of ax over bx squared. And lastly, problem number 4, L 0 to infinity of x sine x over b squared plus x squared squared dx. So these are the 4 problems that we'll solve by solving I, which is very interesting. So let's move forward and solve for I, and then from the solution of I, we can now solve for j, k, and l. So without much, now go to our problem. I being equal to the definite integral, right, of cosine of ax over b squared plus x squared. Right? Let me rewrite this problem as a product of that. Right? And let's focus on this part here. So that part, 1 over b squared plus x squared is equal to the definite integral, or from x equals to, let's say y equals to 0 to y tending to infinity, of e to the power negative b squared plus x squared y, right? Such that when you integrate that, you get something like that, from 0 to infinity, which is equals to that. So we're going to use this guy here and plug it in here. And so I becomes the definite integral from x equals to 0 to x infinity of cosine of ax in bracket definite integral from y equals to 0 to y tending to infinity of e to the power negative b squared plus x squared y, something like that. Okay, now that we have done that, we can change the order of the x and y integrals and have something as follows. So I can also be written as the integral from y equals to 0 infinity, and then now we pull e to the power negative b squared y out, and in here we have 0, so let's have a bracket here, cosine of x times e to the power negative x squared y. So we're integrating with respect to x here, and then close it off with y there. Now, for those who have done Taylor's expansion, would know that cosine of x can be written as the summation from n equals to 0 to n tending to infinity of negative 1 raised to the n times x to the power 2n over 2n factorial. So with that relationship, we can now go ahead and say that integral I is equal to in place of cosine of x, we'll have summation from n equals to 0 infinity of negative 1 to the n, and here what do? We say we have ax to the power 2n over 2n factorial e to the power negative y x squared, the x close bracket, and then we cap off with y. So we can pull this summation out and say our problem now is sum, and this is for the reason that when you're integrating a sum of individual components as the same as the sum of the integration of those individual components. So without loss of any generality, we can interchange or change the positions of the summation and the integral signs. So we have summation negative 1 to the n, and then we can also pull the 2n factorial, and so, and then we're integrating from x equals to 0 to x equals to infinity of x to the power 2n e to the power y x squared and then close off with y. So the interesting bit is now we have a very cool integral here. What is that integral? So let's just focus on that integral for a minute and see what it leads us to. I think the coolest part of this problem is this integral here. Okay, so I'll maybe just change color to just show that this is a sidebar or a side integral. So let's use green, and we have P2n is equal to the integral from x equals to 0, yes, x equals 0 to infinity of x to the power 2n e to the power of y x squared. Okay, how can we re-express that? We can re-express this part as a derivative, right? And you can see where I'm trying to go. I'm trying to go to integration by parts. So this is the same as the derivative of x to the power 2n plus 1 over 2n plus 1, right? And then e. And we're going to use integration by parts, which for us we know, again, this is another sidebar of a sidebar. If you have a product of a function v and a derivative of a function u, and you integrate that, we get the product of uv and u and v, and then we subtract the integral of the product of a function u and the derivative of a function v. So this is a well-known formula for integration by parts. So what do we do now? We know that this is going to be our, based on this is u, so based on that, and this is our v. So the P2n becomes uv is going to be equal to 1. So this is our u, and v is going to be that 0 infinity minus u is derivative of e and this is from 0 to infinity. As we can see here, this is the same as limit as x tends to infinity, x to the power 2n plus 1 e minus limit as x tends to 0 of 1 over 2n plus 1 x 2n plus 1 e. Okay, and then minus the integral from 0 to infinity 1 over 2n plus 1 x 2n plus 1, and this becomes negative y times 2x e negative y x squared. Okay, this goes to 0, this goes to 0. Why? Because as x tends to infinity, this component tends to 0. As x tends to 0, this component tends to 0. So this negative here and this negative can be multiplied together to yield a positive sign there. And then we can pull this constant out. Y is also a constant for us here with this integral. So we have y over 2n plus 1, 0 to infinity. This x, maybe we can even pull the 2 out. There's this 2 here. And then this x times this x, we get x to the power 2n plus 2 e to the power y x squared dx. and this is P2n. So we've come to a point where we've shown that P2n is the same as 2y over 2n plus 1, 0 to infinity of x to the power 2n plus 2 e negative yx squared. Now this part here is the same as P2n plus 2, which means that the integral P2n is the same as 2y over 2n plus 1 times P2n plus 2. We can rearrange things so that P2n plus 2 is the same as 2n plus 1 over 2y times P2n, right? Which is also equal to 2n plus 1 over 2y 2n minus 1 over 2y P2n minus 2, and so on and so on and so on. So what does that tell us? What that tells us is that P of 2n is equal to 2n minus 1 over 2y P2n minus 2, which is equals to 2n minus 1 over 2y times 2n minus 3 over 2y all the way till we have P0. Okay. And what is P0? This is an interesting thing to even think about, because right here I think we have 1 over 2y. So P0 would be equal to the integral from 0 to infinity of x to the power 2 times actually 2 x to the power 0. So let me just delete that for a minute. It's not 2 x to the power 0 times e to the power yx squared, right? Which is equal to 0 to infinity of e. So we could say let's not even worry about that for now. Let's say this is also the same as okay, and since P0 is the same as the integral from e, say let t be equal to t dx is equals 30t is equals to y dx, and so P0 is the same as 0 infinity and actually from here we can say dt over root of y is equals to dx, right, using that. So here we have e minus t squared dt, which is Now this is a popular Gaussian integral. We know that 0 to infinity e x squared dx is equals to root of pi over 2. So from here we can say this is the same as root of pi over square root of y, 2 square root of y. So in other words, our P2n, which was 2n minus 1 over 2y, 2n minus 0 is the same as 2n minus 1 double factorial over, could say this is 2y to the power n times pi over root of y, twice of that. We could also play around and say, okay, could put 2n, we can plug 2n here, can plug 2n minus 2 here, but also in the denominator, and then we pull the 2's out, so in essence we'll have 2n factorial here, and then 2 to the power n, and then pull the 2 out here as well, so we have 2 to the power n, and then below we have n factorial from these guys here because we removed that out, and then we are left with the y, that, and then we have, okay, there's a square root of pi here, square root of pi over 2y half, so 2n, okay, over to the power n factorial, n plus a half, and then we have pi over 2. So I think this is a good point to now say, okay, we have that part figured out, but we could also we can put another 2 here so that this becomes 4, and so we've now derived this to be the p of 2n to be 2 times the square root of pi times 2n factorial over 4n plus 1 times n factorial y to the power n plus a half. So let's begin to define our, we're going to try and substitute for Pn there. So we know our original problem to be this definite integral from x equals, y equals to 0 to infinity of e to the power b squared y, summation from n equals to 0 to infinity of -1 a to n over 2n factorial, and then we had now this p2n, which is okay. So this is the same as 0 infinity e b squared y, summation from n equals 0 to infinity of -1, there's an n here, to the power n, a to n over 2n factorial, and then now we can plug in Pn, which is 2 that 2n factorial over 4n plus 1 n factorial yn plus a half dy. And we can see that that and that would cancel, and we'll keep plugging away and showing that. Maybe let's rewrite this a little bit so that it's straightforward. We can bring this and that, so we have square root of pi divided by 2, and that is this 1 and this have interacted, and then we pull the pi out, so that now we have let's pull the y to the power negative a half out, and then we have that, so that in the bracket or in the summation sign we are left with that, and then we can put a squared, and then 4 I n factorial. So that's a good place to be. That's a good place to be. Let's rewrite our problem a little bit. So we've come to a point where I is equals to root pi over 2, 0, infinity, y to the power negative a half, e b squared y, summation from n equals to 0 to infinity, negative 1 to the n times a squared over 4y rather, to the power n over n factorial. Okay, and is for those of you who are keen enough, you could begin to observe something, and there I'll introduce this guy, right? So this is the same as right? So that's the tail expansion for that. So what that means is that our I now is equals to root of pi over 2 from 0 to infinity, y negative a half e b squared y, and then we can just go ahead and plug e to the power negative a squared over 4y. Okay, which is interesting because now we're beginning to see something of interest. Let's see. So as we have over 2, 0, y negative a half, and then we have now e to the power negative b squared y minus a squared over 4y. So we begin now to see the Cauchy-Schlomlich transformation taking shape for us. And one thing we could do is do a quick substitution. Maybe we can introduce a t there in a bid to take away this guy here. So what do? We said we have I equals to negative b squared y minus a squared over 4y. So we could say let t squared be equal to y, such that 2t dt dy is equals to 1. And so we can substitute for dy with 2t dt, right? Sorry, we had forgotten root pi over 2 there. That will come in handy. So therefore I, and obviously the limits when y tends to infinity or y is equal to 0, t will follow suit. So we won't bother with the limits there. So we have 0 to infinity. And so square root of t squared is, right, so 1 over y, 1 over square root of y is going to be 1 over t. And then we e to the power negative b squared, y is t squared, right, minus a squared over 4t squared, which is good. And then dy is 2t dt. So we have this and that cancel, that and that would cancel away. So we have square root of pi rather, integral from t equals to 0 to infinity of e to the power negative b squared t squared minus a squared over 4t squared. Okay, so we are getting closer and closer. So we've come to a point where we see I is the same as square root of pi times the integral from 0 to infinity of e to the power negative b squared t squared minus a squared over 4t squared, right? And so we can go ahead and re-express this in a certain way. This e to the power negative b t minus a over 2t squared, so we have minus minus, so we'd have to have a minus ab there, because the squares will take, have already been handled up here. But now what about the cross terms? bt times a over 2t, twice of that, which we are now accounting for it there. So we can pull that constant out, and so we have root pi of root of pi minus e to the power negative ab Now this is where now we're going to use the Cauchy-Schlomlich transformation. And what does the Cauchy-Schlomlich transform tell us? Let's write it down. So previously we had we'd shown that if you have an integral from 0 to infinity of a function f of, and you have a x minus b over x squared, that's the same as 1 over a times the integral 0 to infinity of f x squared. And this happens when a and b are greater than 0. So we're going to use that. And it's important for us to note that in our integral there, a, b is actually a. So let's proceed. Since I is root of pi, right? 0 bt minus a over 2t squared 2t, using Cauchy-Schlomlich transform. This is the same as right, and this here is our Gaussian integral, right? So which we won't label so much as to say this is the same as root pi over 2. So we have root of pi and root of pi here, so in other words we get pi over 2b e times that is equals to I, right? So in other words, the I being equal to the integral from 0 to infinity of cosine of ax over b squared times x plus x squared is equals to pi over 2b times e negative that. So we've solved for I, right? And then now we want to now solve for j. We want to solve for k, and we also want to solve for k and l, rather. Okay, so in the next slide, we're going to now show that integral. I mean, for the j, k, and l. We have shown that I being equal to that equals to pi over 2b e, and j being equal to negative of derivative of I with respect to a, which we saw was the integral from 0 to infinity of x sine of ax b squared plus x squared. This is okay, which is equal to negative of pi of 2b times negative b e, right? And then so this and this interact, and then we have that. So this is pi over 2 e. So that is j. Okay, and then k, since we show that k is negative 1 over 2b, to this is 1 over 2b, the derivative with respect to b of pi of so this is a product rule, so what we'll do is we'll pull the pi out and we'll see we have negative 1 over 2b squared e, and then we have negative a over 2b. Okay, so we can multiply this across. We have the common denominator as 4b cubed over we have this plus rather, and so this negative and this negative and this negative interact, so we have 1 plus, we have to keep it ab, we have pi negative ab there. So that is our k. And then we have L, which is equals to negative 1 over 2b, the derivative with respect to b of j, which we found to be the definite integral from x equals to 0 to infinity of x sine of ax over the square of bx plus x squared, right? So which is the same as 1 over 2b, the integral of pi over 2e that, which is 1 over 2b pi over 2 in bracket negative a e negative ab. These signs interact, so we have a pi over 4b negative b. So we've been able to solve for the other three problems just by using the answer that we got with I. So as we end, thank you so much for staying with us. It was an absolute pleasure solving this problem. I hope you did enjoy every single part of it. If you have any questions, please don't hesitate to reach out to us. Also, if you haven't subscribed to our channel, we do really encourage you to subscribe to our channel. For your support and your subscription will go a long way in increasing the profile of our channel. But above all, if you like, please don't hesitate to leave a like. And also, if you know somebody that might benefit from our channel, please do share with them. So without much ado, have a great time ahead, or a great day ahead, and happy Easter to you all.